All right, so here we are with the exponential growth law. So in general, if we have the rate of change of a quantity q with respect to time is proportional to the amount of q present, and q at time zero is equal to q zero sub zero or q naught, then the proceeding in exactly the same way as we did with the previous example, what we can do is we get this theorem one, which is called the exponential growth law. So if dq dt is rq, and remember we kind of did that before, and q of 0 is equal to q0, and what we get is q is equal to q0 e to the rt. So in the last time we said instead of q0 we called it p, and then e to the rt, and this was we called a. So that's kind of what we're doing here. And so again, q0 is the amount of q at time 0, r is the relative growth rate expressed as a decimal, t is time, and then q is our quantity at time t. So now we've got a nice equation we can use for the exponential growth law. Now, the constant r in this law is called the relative growth rate. Now, if the relative growth rate, say, is 0.02, then the quantity q is growing at a rate of dq dt of 0.02 times whatever that q is. So that is 2% of the quantity q per unit of time t. Now, note the distinction between the relative growth rate r and the rate of growth dq dt of the quantity q. If our r is less than 0, what happens is our dq dt is less than 0 and q is decreasing. So with the growth rate one way, we get a growth, but if we have a less than 0, then we're going to get something called decay, and so we'll get an exponential decay, okay? Now, once we know the growth rate is proportional to the amount present, we recognize the exponential growth and can use theorem 1 without solving the differential equation each time. So that's going to be a nice thing. We're going to assume we can recognize it, and we're going to use that the way it is. Then the exponential growth law applies not only to money invested at interest compounded continuously, but other types of problems too, such as population growth, radioactive decay. So that's going to be decay, the depletion of natural resources, probably going to be exponential decay again, and so on. And so that's going to be how we're going to be able to use our growth or exponential growth law to solve these different types of equations. All right. So what do we have here? It says this is the actual problem. It says, assuming the same continuous compound growth rate as in example 1, which is up here, what will India's population be to the nearest tenth of a billion in the year 2020? Well, what we have to do is we have to figure out what our equation is. So if India had a population of 1.2 billion in 2010 at time equals 0, let P represent the population in billions T years after 2010, and assume a growth rate of 1.5% compounded continuously, let's come up with our equation. Well, what's going to happen is our dP dt is equal to what? 0.015 times P. And we said at P of 0, that's 1.2. Okay. So if we go back to our law, it would say P is equal to, well, our R, which is our value here is 1.2 E, because that's our times 0, that's P naught, E to the what? 0.0, oops, not too many zeros. 0.15, and then times our t. So p e to the rt. Well, this is, in this case, this is our p naught at time 0. That's our rate as a decimal, which was the 1.5%. And so now we have that equation. And again, we could have gone straight to it using our growth rate and also our p of 0 is equal to that. But now they want, what is it? They want 2020. Well, that's going to be 10 years after that. So we want P of 10. So that's going to be what? 1.2 e to the 0.015 times 10. So if we plug that into our calculator, I'm just going to do that by hand. So that's 1.2 e to the 0.15. And that gives us, rounded to the decimal, 1.4 billion people. Okay. So that's going to be our solution to India's population to the nearest tenth of a billion in the year 2020. All right, so let's stop there and we'll come back for some more.